So, last time we looked at properties of OK, but as a subset of R to the n. So, we proved that OK is a lattice in R to the n that proved for us that OK is a free Z module of rank n, where n is the degree of k over q, and we defined the co-volume of OK in Rn as discriminant. So, there was an explicit formula in terms of determinant of a matrix, and we proved some properties of the discriminant. So, we are going to study discriminant again throughout this course, but right now we are going to change track and study algebraic properties of OK. So, study OK purely from the point of view of algebra. So, this I will name this section ideal factorization in OK in the ring of integers of k. Okay. So, a fundamental thing that we learn about integers in school itself, even in middle school, is that every non-zero integer or every integer bigger than 1 is a product of primes in a unique way. So, there are two things in this statement. Every integer can be written as a product of prime numbers, and this way of writing as product of prime numbers is unique up to ordering. Okay, and we more or less take this for granted, but it is a highly non-trivial fact, and we use this many times when proving number theoretic statements. Unfortunately, this does not always hold in rings of integers of number fields, or maybe it is fortunate, and that is why the subject is so interesting. So, let me give you an example where prime factorization or factorization into prime numbers fails. So, from a ring theoretic point of view, it's the notion is of irreducible elements. So, let me write that. So, let R be a ring, an abstract ring. So, commutative ring with 1 in it. An element R x of R, an element x of R is called irreducible if x equal to a times b for some a and b in R implies that either a is a unit or b is a unit. Okay, so, these are irreducible elements. So, here is an example in Z. So, if R equals Z, then every prime number is irreducible. Okay. And maybe here I would put another condition, is that x is not a unit. So, I do not want units to be irreducible. Okay. And so, an element of Z is irreducible if and only if it is a prime number. Okay. So, here what we do is we you can do this using unique factorization, but that is not how one wants to do it. Anyway, I will leave this example as an exercise if you have not seen this before. It is not it's slightly tricky if you have not seen it before, but it is good to think about it. So, factorization into irreducible elements does happen in rings of integers, but it need not be unique. So, here let me give you another example. So, what you do is you take k to be q square root of minus 5. Okay. So, this is a number field of degree 2 over q, and we saw last time that the ring of integers of this is z square root of minus 5, right, because minus 5 is not congruent to 1 mod 4, it is congruent to 3 mod 4. And in this we can consider the element 6. You can write 6 as 2 times 3, or you can write it as 1 plus square root of minus 5 into 1 minus square root of minus 5. Okay. So, this is easy to check, but here is something that you need to check: 2, 3, 1 plus square root of minus 5, 1 minus square root of minus 5 are all irreducible elements, irreducible in OK. So, they are not units, and if you write 2 as A times B, then either A has to be a unit or B has to be a unit. Okay. So, and none of them are associated with each other. So, let me write that. So, further, ratio of no two elements no two of these is a unit in OK. Okay. Hence, we get two distinct factorizations of 6 in OK. All right. So, unique factorization fails. Okay. Unique, the slogan that you should take away from this is unique factorization of algebraic integers does not hold in general. Right. Of course, in special situations like for z or zi Gaussian integers it holds, but in general it fails. And now this seems like a hopeless situation. So, what should we do? Well, it was Kumar who found what to do, and he said instead of trying to factorize elements of R into irreducible elements in a unique way, why do not we try to factorize ideals in R into product of prime ideals? And in fact, he figured this out before the notion of ideals was defined, and he wanted to name, he thought of the name ideals because he thought of these as ideal numbers. So, instead of numbers you are looking at ideal numbers. Okay. So, I am not going to recall definition of an ideal because that you have seen in abstract algebra. Let me get straight to the to its application. So, instead of just proving factorization of ideals in rings of integers, we are going to do it slightly more generally. So, the rings in which unique factorizations of non-zero ideals holds are called Dedekind domains. So, let me define Dedekind domains for you, and we will prove properties of Dedekind domains, and then towards later we will prove that rings of integers are Dedekind domains. So, whatever we are going to prove for Dedekind domains will hold for rings of integers of number fields. Okay. So, here is a definition, an important definition. A Dedekind domain is an integral domain R such that it satisfies the following properties. So, one, R is Noetherian. Okay. So, it either it means that it satisfies the ascending chain condition. Another way to say this is that every ideal is finitely generated every ideal in R is finitely generated. So, first of all it is Noetherian and integrally closed. So, we defined this notion some time ago. It is integrally closed in the total ring of, in the quotient field of R. Okay. So, that is the first condition. There are two conditions in it actually, that it is Noetherian and it is integrally closed in the total, in the quotient field of R. And the second condition is that every non-zero prime ideal in R is maximal, is a maximal ideal. Okay. So, every non-zero prime ideal in R is a maximal ideal. These are the two conditions. Of course, this need not hold in every ring. So, let me give you a non-example. If you look at R as polynomial ring in two variables, okay, then X is a non-zero prime ideal but is not maximal, right, because X is contained in the ideal generated by X and Y. It is contained in it, but not equal to it. Okay. On the other hand, it is a Noetherian ring and it is also integrally closed in its total ring of fractions, its fraction field. So, so this just does not satisfy the second property. Okay. So, here are non-examples and we will see later that OK is a Dedekind domain. Okay. So, this is going to be our main results later on, but now we are just going to study properties of Dedekind domains abstractly. Before doing that, let me give you the following proposition, which is satisfying to know. So, here is, you can see, you can think of this proposition as another example of Dedekind domain. So, if R is a principal ideal domain, if R is a PID, which means principal ideal domain, then R is a Dedekind domain, right. So, DD is what I will write for Dedekind domain. Okay. So, how do I prove this? Well, I have to prove three things, right, that R is Noetherian. So, PID is Noetherian, because as I said, one of the definitions of being Noetherian is that every ideal is finitely generated, and in PID every ideal is generated by exactly one element. So, every ideal is finitely generated. Secondly, we need to show that so our claim is that R is integrally closed in QR, right. So, I will recall what QR is. So, QR is a quotient field. So, this is A over B such that A and B are in R and B is not equal to 0 modulo some equivalence relation. So, when are two elements equivalent? So, this is if and only if A B prime is equal to A prime B, right. So, this is the usual way of constructing Q out of Z. So, this is called the total ring of fractions or quotient field of R. So, what we want to do is we want to take let A by B be in QR and integral over R. Okay. We want to show that A by B is actually in R. So, what we want to show is that B is actually a unit, right. Okay. So, we may assume that the ideal generated by A and B in R is 1. Okay. So, this we can always do, because if the ideal, so it is certainly true that the ideal generated by A and B will be a principal ideal, because R is a PID, and so it will be generated by some element C, which means that both A and B can be written as multiples of C, and then we can cancel that C, right. We can divide out by that non-zero C, and we get A and B which are co-prime. Okay. So, the ideal generated by A and B is 1. Okay. And now we know there exists a monic polynomial f of x, which is x to the n plus a n minus 1, x to the n minus 1, and so on up to a 0 in R x, such that f of a by b is 0. So, we can rewrite this as a to the n plus a n minus 1, a to the n minus 1 b, and so on up to a 0 b to the n is equal to 0, right. I am just plugging in a over b in f and then multiplying that equation by b to the n, and so I clear out all the denominators, and this is what I get. Okay. So, what does this tell me? This tells me that a to the n is contained in the ideal generated by b, right. So, you see a to the n is b times something, right. So, it is contained in the ideal generated by b, which means I can write the ideal generated by b as follows, right, which means that the ideal generated by b is same as the ideal generated by a to the n and b, but this contains the ideal generated by a and b to the power n, right. Everything can be in a comma b to the n can be written as a to the n plus b times something, but this ideal is 1, right. So, hence b is a unit in R, therefore, a by b is actually just an element of R, right. So, hence R is integrally closed in QR, right. That is the definition of being integrally closed, that every element in the bigger ring that is integral over the smaller ring is actually in the smaller ring, right. That is what we had defined. Okay. So, that proves the second property. Lastly, we need to prove that every non-zero prime ideal in a PID is actually a maximal ideal. So, let A, so every ideal is principal, right. So, I can just take ideal generated by A, P, a non-zero prime ideal in R. We want to show that A is a maximal ideal. Okay. All right. So, if not, then of course, what will happen is that A is contained in B, but B is not equal to R. So, if this happens, we want to show that A is equal, the ideal generated by A is same as the ideal generated by B. So, what does it mean that A is contained in B? It means that A is B times some C. So, for some C in R, right. Okay. So, what I can do next is right. Okay. So, here I can also assume that B is maximal. Okay. All right. All right. So, if okay, how do I put this? Right. So, the element A is contained in the ideal generated by B, which means that I can write A as B times something, right. That is what it means for A to be contained in B. But on the other hand, this means, so this means that B times C is in the ideal generated by A. We have to use somewhere that the ideal generated by A is a prime ideal, and this is where we are going to use it. So, as A is a prime ideal, either B belongs to A or C belongs to A, right. Now, what happens if B belongs to A? Then this means in this case the ideal generated by B is same as the ideal generated by A, and A is maximal, and we are done, right. That is what we wanted to prove. What happens in this case? Then C is A times D for some D. If I plug this back into this equation, I get A is equal to A times D times C, B, right, which means now we are in the integral domain and A is non-zero. So, we can divide out by A. So, we get 1 is D times B, which means that the ideal generated by B is same as the ideal generated by 1, a contradiction, right. Okay. So, that proves our proposition that any PID is a Dedekind domain. Okay. So, the Dedekind domains are more general than principal ideal domains. Okay. So, there are Dedekind domains that are not principal ideal domains, but every principal ideal domain is a Dedekind domain. Okay. All right. So, our next theorem is the important theorem in this section about Dedekind domains, and it will take some time to prove this, but let me state it. It is good to state this theorem as our eventual goal, and I will prove several lemmas that will go into the proof of this theorem. Okay. Sorry, I should actually tell you something else before this. So, let R be a Dedekind domain. It is not essential to state the theorem, but let me do it this way, and let K be QR. So, the quotient field of R. So, here is a definition of what it means to be a fractional ideal. So, a fractional ideal of R is an R submodule of K that is finitely generated. Over R. So, let me give you an example and a non-example. Okay. So, so R will just be Z and then K is just Q, the quotient field of Z is just Q. Okay. So, fractional ideals of Z are of the form A over B times Z, this is contained in Q, right. So, this is all A over B times N for N in Z. Okay. So, any fractional ideal will be of this form, you can take this as a exercise, and here is a non example. So, if you take A over B, or let me write it this way actually, if I write it as A over 2 to the n such that A is an integer and n is a natural number or 0. So, this is not a fractional ideal. Okay. It is a Z submodule of Q, but it is not a fractional ideal because it is not finitely generated. Okay. So, you are allowing all powers of 2 in the denominator, and so there you can't take a finite set of rational numbers that will generate this submodule over Z. Okay. And I am saying submodule, okay. I can't use multiplicative structure, so I am not saying it as an algebra. Okay. So, this actually the first thing about in this example gives us this general lemma which says that so R is a Dedekind domain and K is simply Q of R, the quotient field of R, okay. And R submodule A of K is a fractional ideal if and only if there exists x in R not 0, so non-zero x in R such that x times A is an ideal in R. So, it becomes an honest ideal in R. So, it is actually contained in R. What are ideals of R? They are R submodules that are contained in R, right. So, fractional ideals should not be so mysterious to you, because we are just saying you take R submodules not necessarily contained in R, but contained in K, right, and K is the field of fractions, that is why the term fractional ideals. Ideals are simply R submodules that are contained in R. So, that is one way of defining ideals. Okay. So, a fractional ideal is something that when you multiply by a non-zero, by a particular non-zero element in R, you get an ideal. So, here is a quick proof of this. So, let A contained in K be a fractional ideal. Okay. So, A is generated by finitely many elements. So, let A1 by B1 and so on up to AS by BS in K be generators of A. Then it is clear what I do, I take x to be B1 dot 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 up to BS. This is an element in R and it is clearly non-zero because it is a product of non-zero elements, right. Okay. And what happens if you take, so any A in A is of the form A is C1 A1 by B1 plus and so on CS AS by BS for C1 up to CS in R. Okay. All right. So, what happens if I multiply it by x? So, x times A, this is C1 A1 by B1 times x and so on up to CS AS by BS times x. And you see x multiplied by, or maybe I will write it like this, x divided by BI, this is in R. Hence, x times A is in R. Okay. So, we have proved one direction, that if you have a fractional ideal, you can get an x. So, that when you multiply by x, you get an and then you just check that this is an ideal. So, and x times A is an ideal in R. Right. So, if you take a submodule and multiply it by a non-zero element, you again get a non-zero submodule. Okay. So, we have to prove the converse. So, if so what is the converse? If x times A is an ideal for some submodule, if x times A is an ideal for some A contained in K, then A is a fractional ideal, right. So, this is the converse, this is the this direction, fractional ideal. Okay. So, it is clear that A is a submodule. So, A is an R submodule of K, right, and I know that x times A is finitely generated, right, because R is a Noetherian ring, as R is Noetherian. Okay. So, let us say that x times A is generated by alpha 1 up to alpha R, okay. Then A is generated by, so here of course x is not 0, right. So, I can and so it is a fractional ideal. Okay. So, this is a good point to stop. So, what we have done today is we have defined what a Dedekind domain is. We looked at examples and non-examples of Dedekind domain. We defined what a fractional ideal of a Dedekind domain is, okay, and we proved that any principal ideal domain is a Dedekind domain. So, next time we will continue studying properties of general Dedekind domains, and our main theorem is going to be factorizations of ideals into prime ideals in a Dedekind domain.